Let us continue our discussion on the modes of a planar symmetric waveguide. In the last lecture, we had obtained the modal fields and propagation constants of symmetric and antisymmetric modes of a symmetric dielectric planar waveguide. Let us now look more carefully at these modes and understand what do they actually represent. Okay. What are the modal fields actually and what do the propagation constants represent. So, for that let me write down the field of, for example, TE0 mode or any symmetric mode. So, it is given in the core or in the guiding film, it is given by E y of x is equal to a cosine kappa x. If I write down the complete solution, that is the z part and t part also, then it would be a cosine kappa x e to the power I omega t minus beta z. Let me expand this cosine kappa x. It is in the same way as I had done for planar mirror waveguide. So, it is e to the power I kappa x plus e to the power minus I kappa x divided by 2 times e to the power I omega t minus beta z. So, let me arrange the terms in a particular fashion and then what I see that this term has e to the power I omega t minus beta z minus kappa x and this has e to the power I omega t minus beta z plus kappa x. So, this is nothing but a plane wave propagating in plus xz direction making certain angle with z axis and this is another plane wave which is propagating in minus xz direction making certain angle from z axis. So, I have this field comes out to be the superposition of two plane waves, one going in plus xz direction, another going in minus xz direction. So, these are the two constituent plane waves and what happens is if I do this kappa square plus beta square, it comes out to be k naught n1 and k naught n1 is nothing but the propagation constant with which a plane wave propagates in an infinitely extended medium of refractive index n1. So, kappa is nothing but the component of this along x. So, if I resolve this in x and z direction, then k naught n1 sin theta will give me kappa. So, it is the component of k naught n1 along x and beta is the component of this k naught n1 along z. So, in x direction I will get from here and here I will get two counter propagating waves and these two counter propagating waves gives me standing wave in x direction. So, the energy stands in x direction, it does not flow out. Okay. However, this standing wave pattern flows in z direction with propagation constant beta, exactly in the same way as planar mirror waveguide. So, these modal fields are the standing wave patterns in x direction because I have E y of x and this is a standing wave pattern, okay, and this E y of x is propagating with propagation constant beta. So, if you look at it again, this E x z t is equal to E y of x e to the power I omega t minus beta z. Okay. Beta is k naught n effective, which basically tells you with what velocity this particular field, this standing wave will propagate. If you remember that in one of the previous lectures I had said that intuitively I can understand the effective index of the mode as effective refractive index felt by a particular field distribution, because the field is now distributed in N1 and N2 regions. So, the effective refractive index would be somewhere between N2 and N1, and that was intuitively correct and that was not rigorously correct. And I see that rigorously N effective is nothing but the velocity with which it will define the velocity with which a particular field pattern will travel. Okay. Rigorously I cannot get from the distribution of power in N1 and N2 regions. Okay. So, this N effective is nothing but N1 cos theta. Okay. So, it is the component of the plane wave k naught N1 in z direction. Okay. And this distribution, the effective refractive index as the distribution of field into two regions, is also not rigorously correct in the sense that I cannot get the effective index from that field distribution in that way. And also if you look at planar mirror waveguide, then you will say that okay, the field is always in N1 region, okay, then why it should have different effective indices for different modes, and why it should be different from N1 or refractive index N. Okay. Similarly, if you talk about radiation mode, in radiation modes the energy is distributed in N2 region, it goes up to infinity, okay, and the effective index for radiation modes, as we will see later, it is less than N2. So, rigorously effective index of the mode is nothing but the component of this along z direction, and it gives me the velocity with which a particular standing wave pattern will travel in z direction. Okay. And since different modes are different in standing wave patterns and constitute different plane waves which are at different angles from z axis, so N effective would be different. Okay. If I look at the condition for guided mode, then it is beta over k naught lies between N2 and N1, okay, and beta over k naught is equal to N2 gives me the cutoff of a particular guided mode. From here what I get, beta over k naught is nothing but N1 cos theta. So, if I replace this beta over k naught by N1 cos theta here, and if I look at it, this cos theta is nothing but sin phi. If phi is the angle which the plane wave makes with the normal to the interface of N1 and N2 regions, then this is N2 less than N1 sin phi is less than N1. Let me divide the whole thing by N1. So, this gives me N2 over N1 is smaller than sin phi is smaller than 1, or sin phi is greater than N2 over N1. This is nothing but the condition for total internal reflection. So, I automatically get that the cutoff condition translates to the condition for total internal reflection. If this angle phi is smaller than, if this angle phi is smaller than sin inverse of N2 over N1, then this wave will not undergo total internal reflection at this interface, and it would be refracted, and the corresponding mode would be radiated out. Okay, it would not be guided anymore. So, this is how I can understand the mode of a waveguide. Let us work out again some examples. Let me consider a waveguide with N1 is equal to 1.5, N2 is equal to 1.46, D is equal to 2 micrometer, and it supports two modes, TE0 and TE1 mode at lambda is equal to 1 micrometer. and if I find out the effective indices of these two modes, they come out to be 1.4905 and 1.4665 respectively. Okay. Now, let me calculate the penetration depths of these modes and the angles of constituent plane waves from the waveguide axis. I know that penetration depth is given by 1 over gamma, where gamma is equal to beta square minus k naught square n2 square, or k naught times the square root of n effective square minus n2 square. So, k naught is 2 pi over lambda naught is given, n effective and n2 are given. So, if I now calculate these gamma for both the modes, then for TE0 mode, gamma is equal to 1.884 micrometer inverse, and correspondingly penetration depth is 0.53 micrometer. For TE1 mode, gamma comes out to be 0.867 micrometer inverse, and correspondingly the penetration depth comes out to be 1.15 micrometer. What are the angles of constituent plane waves from the waveguide axis? Well, I know that these angles are given by n effective is equal to n1 cos theta. So, for these values of n effective, I can immediately find out the values of theta, because I know the value of n1 also. So, for T0 mode, this theta would be cos inverse n effective over n1. So, it would be 6.45 degrees, and for TE1 it would be 12.13 degrees. So, T0 mode is nothing but the superposition of two plane waves making angles plus minus 6.45 degrees from the waveguide axis, and TE1 mode is the superposition of two plane waves which make angles plus minus 12.13 degrees from the waveguide axis. So, after doing the analysis of the waveguide for TE modes, now in the same manner we can do the analysis for TM modes, transverse magnetic modes. If I go back and see that for a waveguide which has confinement in x direction, that is refractive index variation in x direction and propagation in z direction, then the non-vanishing components of E and H are Hy, Ex and Ez, and these three components are related by these three relations. The procedure to obtain the modes and modal fields for TM modes is exactly the same as we had done in the case of TE polarization. So, what I need to do? I need to find out a differential equation, for example in Hy, okay, and solve it. So, to find out the differential equation in Hy, I substitute for Ex and Ez from these two equations into this equation and rearrange the terms. Then I get a differential equation in Hy as d2Hy over dx square minus 1 over n square dn square over dx dhy over dx plus k naught square n square minus beta square Hy is equal to 0. You may see that, you may notice that this equation is different from the wave equation that we had got for the TE case. In the TE case, this term was not there. Excuse me. In the TE case, this term was not there, but here I have this term. So, let us see how do we take care of this. Now, we need to solve this equation for given n square of x to find the modes. So, this is the waveguide which we are considering. Again, symmetric dielectric planar waveguide where n of x is given like this. Procedure is again the same, that I need to write this equation in this region and in this region. So, I do this for mod x less than d by 2, I get this equation. Why? Although I have this term in general for a variation n square of x, but when I write this equation in the individual regions in this kind of a step index waveguide, the refractive index is uniform, okay, and when the effective index is uniform in this region, so this term goes off. So, I have got this equation for mod x less than d by 2 and this equation for mod x greater than d by 2, and you can see these equations are exactly the same as we had obtained in the case of TE polarization. So, again I define this as kappa square and this as gamma square, and since I am interested in guided modes, so kappa square and gamma square are positive. So, these are the equations and the solutions are again the same, exactly the same. H y is equal to a cosine kappa x plus b sine kappa x for mod x less than d by 2, and the decaying solutions for mod x greater than d by 2. And again a, b, c and d can be determined with the help of boundary conditions. In this case also I can make use of the symmetry of the problem and divide these solutions into symmetric and anti-symmetric. So, for symmetric modes my h y would be a cosine kappa x in the guiding film and c e to the power minus gamma mod x for mod x greater than d by 2, that is in these regions. So, what next? What I should do? Now, I should apply the boundary conditions to this kind of modal field. And what are the boundary conditions? The boundary conditions are again the same. The tangential components of E and H should be continuous at x is equal to plus minus d by 2. What are the tangential components here? Well, if I look at TM modes, the non-vanishing field components are Hy, Ex and Ez. So, the components which are tangential to x is equal to plus minus d by 2 planes are Hy and Ez. So, Hy and Ez should be continuous. How Ez is related to Hy? We look at this. So, Ez is related to Hy with some constant times 1 over n square dhy over dx. So, this because this n square depends on x, so I should take it to that side. So, now the boundary conditions give me Hy and 1 over n square dhy over dx should be continuous. So, this is the difference with the TE case. Okay. In TE case I had the boundary conditions, the boundary condition led to Ey and dEy over dx should be continuous at the boundaries, but here I have Hy and 1 over n square dhy over dx should be continuous at the boundary. So, I apply these. So, first I apply that the field should be continuous, Hy is continuous at x is equal to let us say plus d by 2. So, a cosine kappa d by 2 is equal to c e to the power minus gamma d by 2, and then I apply this 1 over n square dhy over dx should be continuous at x is equal to plus d by 2. Then it is on this side I have 1 over n square minus a sine kappa d by 2 is equal to minus 1 over n2 square gamma c e to the power minus gamma d by 2. So, this gives me the transcendental equation. If I divide this by this, kappa tan kappa d by 2 is equal to n1 square over n2 square times gamma, or by multiplying with d by 2 on both the sides I get kappa d by 2 tan kappa d by 2 is equal to n1 square over n2 square times gamma d by 2. So, this is the transcendental equation. The difference is this factor. I have this factor n1 square over n2 square extra in the case of Tm polarization. So, for symmetric modes, if I now convert this equation into xi and v, then I know xi is nothing but kappa d by 2. Then in exactly the same way as I had done for T case, for symmetric modes I will have the equation as xi tan xi is equal to n1 square over n2 square v square minus xi square, and this is the field. Similarly, for anti-symmetric modes, the equation would be transformed to minus xi cot xi is equal to n1 square over n2 square root of v square minus xi square, and this is the field. So, the transcendental equation is this. So, if I use the graphical solution to solve this, so I should equate this, the right hand side and left hand side both to eta in this case as well as in this case. So, for symmetric mode I will have eta is equal to xi tan xi, and for anti-symmetric case I will have eta is equal to minus xi cot xi, and from the right hand side I will get xi square over v square plus eta square over v square times n1 square over n2 square whole square is equal to 1. Okay. In the case of TE modes, this factor was not there and I had the circles here, xi square plus eta square is equal to v square. But now I no more have circles, but this is the equation of an ellipse. Okay. So, I have ellipse here, and what is the major axis of the ellipse? It is along eta. Okay. So, what I will have to do now, to have graphical solutions, I will have to plot these two together for symmetric modes and these two together for anti-symmetric modes and look for points of intersections. So, I do this. So, again these red curves show eta is equal to n1 square over n2 square xi tan xi, and so this is for symmetric modes, this is for anti-symmetric modes. Okay. Sorry, this is eta is equal to xi tan xi, it is eta is equal to minus xi cot xi. Now, these solid lines represent the circles xi square plus eta square is equal to v square and correspond to TE modes, while these ellipses which are represented by dotted lines, they are the ellipse corresponding to the TM modes. Okay. So, these are the ellipse corresponding to TM modes. What I see here, if I take a particular value of v, and see the points of intersection of these TE and TM modes, then it should not be V naught, it should be V. So, for example, for V is equal to 6, the point of intersection corresponding to TE mode is somewhere here, and for TM mode it is at slightly larger value of xi. So, what I have for a given mode, whether it is m is equal to 0 or m is equal to 1 or m is equal to 2, xi for TM mode is always greater than xi for TE mode. And since xi is equal to kappa d by 2, which is d by 2 square root of k naught square n1 square minus beta square, then beta for Tm is always less than beta of Te. In terms of normalized parameters, in the same way as I had done for Te case, I can also write down the transcendental equation for Tm modes, symmetric and anti-symmetric. So, equations are similar, only thing is this extra factor of n1 square over n2 square in both the cases, symmetric and anti-symmetric cases. Cutoff conditions. What are the cutoff conditions? Well, beta over k naught should be equal to n2, which means b should be equal to 0. If I put b is equal to 0 here and here, I will get the cutoff conditions for symmetric and anti-symmetric modes, and you can see that since b has to be 0, if I put b is equal to 0, then this factor is absorbed here in 0. So, it would not have any effect, on the cutoffs. So, for symmetric modes, the cutoff condition remains Vc tan Vc is equal to 0, and for anti-symmetric mode it remains Vc cot Vc is equal to 0. So, in general I have the cutoffs for TM M modes as Vcm is equal to m pi by 2, which is the same as in the case of TE modes. Okay. Let us now plot V curves. So, that I will have to plot for a given value of n1 over n2. Let me see how does it look like schematically for n1 over n2 is equal to 1.5. So, the first thing is the cutoffs are the same. So, the plots will start from the same value for TE and TM. So, if I plot it for TE 0 mode, then for TE 0 mode it both will start from 0 because they have the same cutoff. So, TE 0 mode goes like this and TM 0 will also start from here, but whether this curve would be below this or above this, and I see that since the propagation constants of TM modes are smaller than the propagation constants of TE modes. So, the curve corresponding to TM mode would lie below the curve corresponding to TE mode. So, it will go like this. For m is equal to 1, so this would be TE1 and this is TM1, similarly TE2, TM2. Again these curves are universal for given value of n1 over n2 now. Okay. So, here I should also take care what is this ratio n1 over n2. Modal fields. If you look at modal fields, then again in the same way the modal field for TM0 would look like this. This is for low index contrast waveguide, okay, and for TM1 mode it looks like this. What I should take care here is, and what I should pay attention to is that in case of TE polarization, EY and DEY over dx was continuous. So, the field as well as its slope was continuous at the boundaries x is equal to plus minus d by 2. But you remember that in TM polarization, Hy and 1 over n square dHy over dx are continuous at the boundaries. So, the slope is not continuous, although here I see that the slope is also continuous at the boundary, okay, but rigorously it is not continuous. It is the discontinuity in the slope is so small that it does not show up, because if you look at n1 and n2 are very close. So, if it is weakly guiding, if the waveguide is weakly guiding, the n1, the values of n1 and n2 are very close to each other, then that will not show up here. If on the other hand, if I plot this for high index contrast waveguide, you now look at the values of n1 and n2, the factor n1 over n2 is now 3.5. Now, if I plot the modal fields for T0 mode are like this. There is no discontinuity in the slope, while here this discontinuity shows up because the factor n1 over n2 is very large. So, this is the first thing I will see. Similarly, in the case of TM1 mode, there would be huge discontinuity. Again, just as in the case of TE modes, in TM modes also, mth TM mode will have m number of zeros. And since the propagation constant of TM mode, this is wrong, it should be beta Tm is less than beta Te, please make correction. So, the penetration depth of TM modes are larger, okay. You can see the penetration depth of TM modes are larger than the penetration depths of TE modes. I can look at some examples. If I consider this waveguide with n1 is equal to 1.5, n2 is equal to 1.46, d is equal to 2 micrometer, at lambda is equal to 1 micrometer, n effective of T0 mode comes out to be this, and of Tm0 mode comes out to be this. So, you can see if the index difference is very small, Te0 and Tm0 modes have nearly the same propagation constants, okay, very close to each other. And if I now calculate the penetration depths for the two modes, the penetration depths are also very close to each other, 0.5305, 0.5329, difference is only about 0.45%. But if I take high index contrast waveguide where n1 is 3.5, n2 is 1, then n effective of T0 mode is 3.1916 and that of Tm0 mode is 2.92. So, which is very different, there is a huge difference between the propagation constants. Now, if I calculate the penetration depths, then the difference is about 10.5%. With this, I have done the analysis of dielectric planar waveguide for symmetric modes as well as anti-symmetric modes. I have calculated the propagation constants, I have found out the modal fields, their behaviors, penetration depth. The only thing that remains is how much energy do they carry, how much energy, how much power these modes carry. We will go into that in the next lecture. Thank you.